Soil physical properties are the subject of this webinar, which is part of the Soil Health Bootcamp webinar series. Soil health is defined as the capacity of a soil to function, and there are many physical, chemical, and biological properties that could be measured as a way of defining or understanding soil health. So what is a soil function? Plant productivity is a very good indicator that a soil is functioning properly, but some of the other functions that soil provides are nutrient cycling, diversity for microbes. There are many beneficial microbes that live in soil, either providing services to the plants, but I can also think of several examples where beneficial medicines have been developed from soil microbes. And then environmentally, soils provide many services in that they regulate and partition water flow, and they filter, buffer, degrade, immobilize, and detoxify organic and inorganic materials. So I often think of soil, plants, and microbes as a recycling kind of relationship. So soil and plants are related. Plants obviously use soil as a way to anchor their roots, and soil provides the storage of water and nutrients for the plants to use throughout the growing season. Plants and microbes are very related. So microbes decompose plant tissue, providing nutrients at some point during the growing season, and there are specialized relationships between plants and microbes, such as rhizobia, and another relationship would be mycorrhizal fungi. So not all plants are mycorrhizal, but for those that are, plants would be providing carbon to the microbes, and the microbes would be providing phosphorus to plants. And then soil and microbes are interrelated in that microbes use the soil as habitat, and in doing that, improve soil structure. That also goes back to the decomposition of plant materials. So as microbes decompose plant materials, they create organic matter, and organic matter is almost the governing property. If you could do one thing, improving soil organic matter tends to lead to improvements in all physical, chemical, and biological properties of soil. So I'm going to focus on soil physical properties and with special attention to precipitation capture and storage, and also be looking at physical soil properties we can measure, and keeping in mind that some of the effects of soil degradation can be reversed through certain management practices. So this is a dramatic picture of a raindrop hitting a soil surface, and you can see the splash of the particles, which could actually go several feet. So because of this impact, we can get crusting because the soils, the aggregates are being destroyed. And so the result after a rainfall on a bare soil might look like this. There's crusting. You can imagine seedlings having a hard time emerging through that crust if it happened right after planting. There would be limited water movement into the soil profile with subsequent rains. There's also diffusion of gases that needs to happen between the soil and the atmosphere. So roots respire. Plant roots use oxygen and they give off carbon dioxide, just like people. And so oxygen needs to be able to diffuse into the soil, and carbon dioxide needs to be able to leave the soil. So after crusting can come erosion. So with a subsequent rain on a crusted soil, soil could be lost from the field, and we're not just losing sediment, but sediment is also there could be phosphorus and other things attached to those soil particles. So it's a loss of soil from that, from a place where it's useful, and it could end up in a place where it's undesired. So in water, it could pose water quality problems. Wind erosion is another common way to lose soil, and that could have a couple of negative effects. So seedling death could come from abrasion of sand on the soil particle or on the plant tissue, and also later in the season there could be damage to produce, reducing its marketability. So soil structure and aggregation, I'll show data on aggregation in a moment, but soil structure is the way that the sand, silt, and clay particles are arranged. So there are inherent soil properties. We can't change the structure again, so we can't change the texture. Texture is the amount of sand, silt, and clay. We call that an inherent soil property. You inherit it. So, but what you can change is something that has to do with the way those particles are arranged. So structure is the arrangement of sand, silt, and clay particles into PEDs, or into bigger pieces, structural units. And that can be done with organic matter. It can also be done by reducing tillage and also time. So on the left, I took this soil sample from a very well aggregated soil, a no-till field. It had been no-till for many, many years. So the only soil disturbance that happens in this particular field is at planting time. So a planter might come through, open up a slit into the soil, drop the seed in, and close it again. And on the right side is a soil right over the fence row that has been tilled for decades and decades with multiple passes of tillage implements. And so you can see the difference in, imagine pore space. How would water act if it flowed through either one of these soils? So one way that I measure the structure or the aggregate stability is in the laboratory using a property called mean weight diameter. And so I use a nest of sieves, so a big stack of sieves where the largest holes are at the top and the smallest holes are in the lowest sieve. And I add soil to the top of that sieve and then wet that. And so the whole stack moves up and down in water, and then I measure how much soil comes out on each sieve at the end. So what I'd like to see is more soil staying on the upper sieves, so bigger pieces, versus less soil leaving that bottom sieve and making the water muddy in the bucket. So if you think about that, it's kind of like a grade point average. The more A's and B's you get, the higher your mean weight diameter grade point average would be. And D's and F's would be very, very small numbers. You'd have a low grade point average. And so it looks like this. This is from a study done involving cover crops and pumpkin production, and this graph is from a site sampled in Wichita at the John C. Pear Center in spring 2015. The y-axis are the mean weight diameter, and that's in millimeters. So in this case, for this graph, larger is better. You want to see a larger value. So tillage is in the purple, and it's got a mean weight diameter of about 1.5 millimeters, so small. And then the orange bars are for cereal rye, and that's either alone or in combination with some other cover crops, and those values are quite a bit higher, closer to 5. And then oat alone, or oat pea mixture, I should say the oats are the last two combinations here of oat and oat and pea, those would be planted in spring, and the cereal rye treatments would be planted in the fall. But either way, they provided a lot of cover, and you can see if I click again, now there are letters of significance that appear over the top. So it defines groups. So the tillage treatment is by itself, and it's small. The value is small, and all the other treatments cluster together, meaning that there's no difference between any of these cover crops with respect to the fact that they all create larger aggregates. And this is a small p-value, so scientists would quite often use 0.05 as their cutoff. We'd like to see a value smaller than 0.05 to decide that this is very significant. And so again, the point of this is to show that there are technical ways we can measure how stable soil is to disruption by water, or which can be an approximation to erosion. But there is a simple method that you can do. So here I went and found soils that were very, very similar in every way except for one thing, and that is how they're managed. So they're all located very, very close in space. I mean, no more than a few 100 feet apart. And I filled up some beakers with water, and there's nothing special about how much water is in each one. I just tried to make it similar. So one is labeled conventional, so a soil that is very frequently tilled multiple times per year for many, many years. The center one is from a no-till field, so it hasn't been tilled other than at planting time for many, many years. And native, this soil on the right has never been tilled as far as we know. There's mature prairie vegetation growing there. And so I took equal sized pieces. Now drop them in water. So from the side, perhaps the no-till and the native, they don't look much different. The conventional till, some pieces are falling off. But when you drop pieces of soil um, in water like this, the first thing that happens is water tries to rush into those pores and the air is trying to get out. So for no-till and the native, what's happening is that there's pores that have been developed, so spaces and pores. So imagine a plant root growing and growing through this year and then next year decomposing. Well, that's left behind a long tunnel. So if air is trying to get out of this long tunnel, it can go out one side as the water's coming in the other side. Same for the native. Now for the conventional, if we don't have any long channels that have existed because this has been tilled recently and so there's very little structure, when air's trying to get out and water's trying to get in, what happens? Well, there's an explosion. So this is called the exploding aggregates test. So I haven't swirled these, I haven't disturbed these in any way. And you can see from above, this center one, this no-till, there's an air bubble just about to escape and pop. But they're very stable. The air's escaped and the aggregates pretty similar to when they were sitting outside the beaker. And over here it's definitely exploded and fallen apart for that reason. The air has exploded out because the water was not able to enter slowly. It just entered all at once. There was no long continuous pores. Okay, so there's relationships between physical properties, and I'll say that organic matter is key. So whenever organic matter is higher, soils are more forgiving. So in this case, I'm showing two comparisons. This is from a long-term study that I did, but that CT means conventional tillage. Again, lots of tillage multiple times per year for multiple years, and no-till. This one hadn't been tilled for more than 30 years at the time we sampled this, and the depth here is in centimeters, and so there's 2.5 centimeters in every inch. So this one is about 1 inch measurement, and this one's down at about 3 inches, and so forth. So the 135 means that the two had gotten the same amount of nitrogen, which is a lot of nitrogen, and this was used for producing a row crop. And so where the no-till has accumulated organic matter near the surface, so it has an organic matter of maybe 3% versus the conventional till has about maybe 2.2% organic matter. And so they're quite different. And how does this relate to soil physical properties? Well, if I put this graph up where it's bulk density, they kind of flip-flop. So the no-till has higher organic matter and has lower bulk density. Well, soils, this is a case where we want to see a low value for bulk density. The less density is more means that if the density is high, the porosity is low. So I'd rather see for plant production low density so that there's lots of pores like I said, for water exchange, for gas exchange, and so on. So they're interrelated. High organic matter means that the density is low, so porosity is high. And for soils, for every different texture, again, texture, these are the soil properties we can't change. We can't change the amount of sand, silt, and clay we have, but we can change the organic matter. And soils with more organic matter have better aggregation. Better aggregation means soils are less compactable. And again, if you knew your soil's texture, so perhaps a silt loam, 1.55 would be the maximum. That's the point at which you'd start to see issues with root penetration. So soils that are compacted or have poor physical properties often the plants have signs of stress. So whether they look like they're drought stressed or they might look like they're nutrient stressed, even though there might be plenty of nutrients there, if the roots can't penetrate through a dense soil and get to those nutrients, it's going to look like a deficiency. So this graph shows infiltration, which is the movement of water into soil. And to do this, I pounded a ring, so it was a 6-inch irrigation pipe, so 6 inches tall, 6 inches wide. I pushed it into the soil halfway, so it goes in 3 inches. And then I very carefully add an inch of water to that. And so in this case, the more minutes it takes, that's kind of a bad thing. So in this case, for the conventionally tilled comparison, it took 25 minutes to infiltrate 1 inch of water into the soil. And the other treatments, on average, none of them took more than 15, and most of them took less than 10 minutes to infiltrate that same inch of water. In this case, there's no statistical difference. The p-value says 0.14, but again, the tendency, the trend is that it is lower. The infiltration was faster. So you could imagine this is ponded infiltration, but even if there was a rainfall event happening, these soils would be able to accept it more, and there'd be more storage. There'd be a longer time before water started running off of these cover crop treatments versus off of this tilled treatment. So, and with that, that concludes this presentation on soil physical properties, and again, as a part of the webinar series, Soil Health Bootcamp.